A technology lead at a regional insurance company spent 3 months in 2023 evaluating whether an open weight model could handle their claims processing workflow. The answer at the time was no. The best available open weight models at a practical size produced output that required too much correction to be operationally useful. The team moved to a commercial API and built their workflow around it. 18 months later, a compliance audit flagged the arrangement. Customer claim data was leaving the organization at every inference call. The commercial API they had chosen did not offer a self-hosted option at their contract tier. Rebuilding around a self-hosted model was now a 9-month project instead of a 3-month one. The landscape had shifted in their favor. They had not noticed. This is The Model Landscape Has Shifted. Models Part 2. Open weight models close the gap. What that means before you pick one. Section 1. Why this matters before anything else. Every article in this arc assumes that you're making a deliberate choice to run a language model on infrastructure you control. That choice used to mean accepting a significant capability penalty. It no longer does for most practical use cases. Understanding what changed and why it changed your options is the foundation every subsequent decision in this arc rests on. Model selection, hardware requirements, RAG versus fine-tuning, deployment architecture. All of it depends on knowing what the current landscape actually looks like rather than what it looked like when most of the guidance you will find online was written. Section 2. What changed? 3 things shifted the landscape material between 2023 and 2026. First, model quality at smaller parameter counts improved faster than anyone predicted. The assumption that a useful language model capability required hundreds of billions of parameters was wrong. The 7 billion to 14 billion parameter range now produces output that handles a wide range of production use cases without the infrastructure footprint that larger models demand. A model that runs on a single consumer GPU in 2026 would have required a small data center in 2023. Second, training and alignment techniques matured. Early open-weight models were capable but inconsistent. They required significant prompt engineering to produce reliable structured output. Instruction tuning and reinforcement learning from human feedback applied at scale to smaller models closed that reliability gap substantially. The models are not just more capable, they're more predictable, which matters more in production than raw benchmark performance. Third, the ecosystem around open weight models caught up. Tooling for quantization, serving, fine-tuning, and evaluation that previously required deep expertise is now accessible to practitioners without research backgrounds. Running a quantized 13 billion parameter model on a machine you already own is a documented, repeatable process in 2026. This was an experimental one in 2023. Section 3. The current families worth knowing. The open weight landscape has consolidated around a smaller number of model families that dominate practical deployments. Meta's Llama family remains the most widely deployed open weight foundation. Llama 3 and its derivatives have extensive community support, broad tooling capability, and a permissive license for most commercial use cases. The 8 billion parameter instruction variant is the default starting point for most first deployments. Mistral and its Mixtral variants introduced mixture of experts architecture to the accessible open weight space. Mixtral 8x7b delivers performance comparable to much larger dense models by activating only a subset of parameters per inference call. For teams with constrained hardware, this architecture offers a meaningful capability for compute dollar advantage. Qwen from Alibaba has emerged as a serious contender, particularly for structured output tasks. The benchmark results in the research community consistently place Qwen 2.5 variants above equivalently sized models from other families on extraction and reasoning tasks. For a pipeline that needs reliable structured output, as the NOAA use case in this arc will, Qwen warrants serious consideration. Gemma from Google and Phi from Microsoft round out the landscape at the other end. Both families prioritize efficiency and are optimized for deployment on constrained hardware. Phi 3, in particular, has produced results that challenge the assumption that parameter count is the primary driver of capability. Section 4. Commercial self-hosted is a real category now. The binary between public API and open weight self-hosted has a middle option that did not exist at meaningful scale 2 years ago. Several commercial model providers now offer deployment arrangements where the model weights run on your infrastructure under a commercial license. You get vendor support, guaranteed update paths, and in some cases, fine-tuning services without sending inference traffic through a third-party API. The trade-off is cost and licensing complexity versus the operational overhead of managing open-weight models without vendor support. For organizations in unregulated verticals where open-weight licensing creates legal uncertainty, or where internal teams lack the expertise to manage model updates independently, commercial self-hosted is worth evaluating alongside the open-weight options. We cover this in detail in Part 6 of this arc. Section 5. What this means for the build. This arc builds a purpose-built language model on infrastructure you control. The NOAA Storm event dataset is the through line. Every layer of the stack, from data ingestion through deployment and monitoring, gets built explicitly with Claude Code prompts at each step. The model family you choose shapes hardware requirements, tooling choices, and fine-tuning options downstream. This article does not make that choice. It maps the landscape so the choice in Part 5 is informed rather than arbitrary. The landscape shifted. The build was not practical 18 months ago, it's practical now. The rest of this arc is how you do it. Next, before you install anything or download any weights, you need to know whether your hardware can run this and what it will cost you to find out.